body composition, gender, and physiological age differences on potential lower limb injury during forced loading. The aim of this study was to determine the effect gender, age, or body mass have on increased limb stiffness. Increased limb stiffness has been shown as a direct cause of future injury. Therefore, we're looking at the effects gender, age, and body mass have on possible future injuries. Stiffness is the deformation of the body in an applied force. So an applied force is acting on the body and it's got to dissipate that force. The dissipation of the force is generally done through muscles, ligaments, tendons, and through bone structures. There are differences, it's been found, between males and females in stiffness. Hughes and company found that females displace more energy through the quadriceps and soleus than males. Now, whilst this takes a lot of pressure off the lower limb ankle area, it incurs a penalty because females are 9 times more likely to do an ACL or a knee injury than males. On the other hand, males show greater stiffness in the lower limbs. They displace their ankle more than females. This means they're obviously more susceptible than females to lower ankle injuries. As we age, can be seen in the lower limbs through a decrease in muscle mass, through decrease in ligament and tendon water composition. Now this water allows more elasticity of the joint, plus we can see a decrease in bone density. Now more density means stronger, less density means it's weaker, and forces acting upon it have a greater chance of inflicting injury. In a study by Berthart and company, they found that peak performance was computed to be 26 years old. That's when males and females are at peak physiological and mental performance. BMI is a surrogate fat measure. It was created in the 1830s but still holds some significance today. We're going to use BMI to show the difference in weight. Now, with the BMI measures, optimum weight is under 25, whereas overweight and obese is over 25. When looking at BMI, we need to divide weight, so an individual's weight in kilograms, divided by their height, squared. Participants stepped off a 40 centimetre high box with no shoes on, onto an AMTI force plate. We wanted to randomise the order to stop bias testing, so we placed 2 pieces of paper, one with left, one with right, on the bench next to the force plate. Participants chose which one they wanted first, and whatever answer they got, left or right, was the leg that they first stepped off with. When we were measuring peak ground reaction force impact, we do this in Newton kilograms. This data from the AMTI force plate was then transferred to Microsoft Excel to record for our statistical data. When we started our statistical analysis, participants were separated into groups: gender, age, and BMI, and then subgroups of these groups. Gender was male and female, age was below peak age, below 26 years old, or above peak age, above 26 years old. BMI was calculated, so optimum weight below 25 on the BMI scale, or overweight or obese above 25. For the results, we found that participants' mean score of peak ground reaction forces measured in Newton kilograms was 2,788.9 with a standard deviation of 695.3. In the top left and right hand corner of this screen, you can actually see one of the participants on the used AMTI force plate. Males and females, when compared to peak ground reaction forces, showed a lot of difference between their forces. Males showed statistical significance to have higher impact forces than females. Now, older participants show a weak and positive relationship with lower limb stiffness. They show that it's not significant because P is greater than 0.5, but there was increased lower limb stiffness in older participants. Like older participants, overweight participants were found to only have a weak moderate correlation between peak ground reaction forces and their weight. So this shows that overweight may cause higher ground reaction forces, however, this was not a significant relationship. Next in the results, we divided males and females with other groups. In this stage, we divided males and females with peak age under, peak age over. What we found was males above 26 showed significant relationship with lower limb stiffness. Now, the alpha level was 0.5, showing this significance. Overweight males showed moderate positive correlation, R is equal to 0.58, and female BMI value was quite low of 0.09. We would have expected this to be quite higher. What we found was males have less lower limb elasticity in the lower limb muscles and tendons. This may be caused because of increased weight. Previous studies by McGill found that an increase in weight does affect the elasticity of the muscles. What we did find also is that women have more elasticity than men. Now, this isn't a shock. We do expect this because previously we just discussed how weight can affect. Women are lighter, but women also increase the activation of the quadriceps and soleus. Now, this takes more dissipation of ground reaction forces. However, the dissipation that's seen in the ankle is then transferred to the knee. What we also found was participants above peak age had increased lower limb stiffness. This may be caused because the degeneration of muscles, ligaments, tendons, bone. When stepping from a height, young males were seen to use more muscle and skeletal system, whilst older adults were seen to use more skeletal. The reliance on the skeletal system for older males shows a direct cause and effect of degeneration as we get older in the ligaments, muscles and tendons. The reliance on the skeletal system is to dissipate the impact of force placed on the joint, hence increasing peak ground reaction forces. Leg stiffness increased as weight increased. The heavier you were, the higher your ground reaction forces were. Now, there was little change in all female participants for all categories, gender, age and weight. This could be because of the talked about activation of the quadriceps and soleus and taking the weight off the lower limb areas. The young age of participants may have affected our data as well. We're thinking possibly women who have been through menopause may show more significant degeneration of lower limbs because this causes less muscle elasticity, less tendon elasticity, and less bone density. So this might show accurate data. Our study shows a clear, significant relationship between gender, age, and body mass causing increased risk of injury for males only. Females show a lower risk of ankle injury because of the activation of quadriceps and soleus, but because of this have a higher risk of knee injury. Practical implications. Professionals can use this information to effectively show a exercise regime or stretching regime which can, for age participants, stretch out the ligaments causing more elasticity, or for high body mass participants, they can use this data to show that if they lose weight through healthy eating and exercise, the elasticity of the joint may come back because the heavier you are, the higher the ground reaction force. Are there any questions? These are just the references used in the presentation.